In professional IT, containers have undoubtedly become one of the most crucial technologies we are using these days. No matter if you are a cloud engineer deploying high available container orchestration, a software developer coding and shipping apps, or a sys administrator deploying and maintaining app services, containers are just everywhere. And I think this is such an important technology that everyone in IT should know about. Hey everybody, this is Christian, and in today's video it's all about Docker and containers. You probably know from my other videos here on YouTube that I often use Docker and other container orchestrators to deploy and maintain application services in my home lab. So most of you might be quite familiar with it, but I just noticed that I really didn't create a comprehensive tutorial series about this important topic yet. So that's why I want to start a brand new video series starting with today, where we unveil all the magic behind Docker and containers. I've prepared some interesting presentation with a lot of background information for you to understand the bigger picture in IT, but also many practical examples and walkthroughs you can directly follow along in your terminal. So no matter if you're just a beginner curious about Docker and you just want to learn more about it, or you're somewhat advanced and experienced but you want to get more background information, so this is definitely the right video series for you. So I hope you join me on this journey, and I hope that will be a lot of fun. But before we start, I first want to show you Kestra, an absolutely incredible IT automation tool, and thanks Kestra, by the way, for supporting this video. Now, I've been playing around with this tool for quite a while in my home lab. It's mainly created for automating data operations and building reliable workflows. For example, I've used it to create some automation workflows that run updates on my servers, or perform container image build tasks, or CI/CD pipelines to easily deploy and update software. Now, what makes Kestra very interesting in comparison to other automation tools like Ansible or Terraform is that Kestra comes with a really nice web UI that is both developer and non-developer friendly. For example, if you like to create automation pipelines, you just write your workflow logic in a declarative YAML-based language, but it also allows non-developers to have a visual representation of what's actually happening inside the workflows, with the ability to easily change values or optimize queries, even without having to write any line of code. And because I know you guys love free and open source tools, yes, it's fully open source, and you can easily deploy this in your own infrastructure using Docker, Kubernetes, or whatever you like. The free community edition gives you all the necessary core utilities to build, schedule, and run automation workflows. And if you like to get some additional enterprise features, just reach out to the Kestra team and book a demo. You will find a link to this tool in the description of this video. Just try it out, it's a really great tool. Okay, so before we start with the practical walkthrough and I show you how to deploy containers, I first want you to understand the bigger picture of why do we actually use containers in IT. And I just want to show you a quick example. So if we want to install an application on our machine, we would typically install that on an operating system, which might be Windows, Linux, server, it doesn't really matter. And when we install an application, that usually requires a lot of things to be present on the operating system. For example, if that application one is written in a Java language, it always requires the Java runtime environment to be present on the system. And just like that, the application one might have other requirements, such as an SQLite database to store some data for this app and so on. So that mostly works totally fine as long as all the packages are installed on the operating system. However, if you start installing other applications on the same system, they also might have different requirements. If the application 2 is also written in Java language and the installer might decide, hey, I need Java, but in a slightly newer version, from version 16.2 to version 17 LTS, you never really know. So if application 1 also works with the latest version of Java, version 17, so maybe the application 1 hasn't been updated by the developers to be compatible with it, or maybe it has an update, but the system administrator hasn't updated the application yet, so it starts crashing and you get a problem on your system. So this is a very common we see in Linux distributions, for example. So that's the whole reason why we have package managers. They try to solve all these dependency issues, and you can definitely see that Yeah, that's quite a huge challenge, yeah, for both developers, because developers need to make sure that their application is always working in all of the different edge cases with different systems, with different binaries, libraries. It's a hell of a lot of work. And also for the sys administrators, you can imagine this is quite a heavy task to always make sure all your apps are functioning properly if you're doing updates. So if you have once worked as a sysadmin, you probably know what I'm talking about. And you can imagine that even gets worse and more challenging the more application you install on the operating system. And this is exactly the problem why we use containers. The idea behind containers is, so if we have all these dependencies, why don't we create an isolated environment for each application and ship the application with all its required dependencies, libraries, binaries, and utilities in its own package, and that should not interfere with other containers on the same system. So when we install the application 1, the container 1 where this application is installed and deployed has also the Java runtime environment in version 16.2 and the SQLite database. But if we create another container with application 2, that also has a Java runtime environment present, but in a different version, and container 1 and container 2 actually don't know about each other. So we ship all of these libraries, dependencies, and utilities along with the application in its own container package, which is very lightweight and very efficient. And this is what we would call a container image. And from that container image, we could create multiple copies and create more than one container instances that are all running in their own isolated and protected environment. So that is the whole idea behind containers. And you can imagine this has a lot of great benefits and advantages for both the software developers and the system administrators, because if a software developer needs to write new code for the application 1, you don't always need to make sure that your app works with every Java version that is out there. You just create your container image and package your desired Java version that your application is compatible with along with your container image, provide that to the system administrator, and the system administrator don't need to care about if the server has Java runtime environment installed in the correct version. The system administrator can just start the container, and you can always be sure that the container image has all the exact dependencies, binaries, utilities, just like the developers have packaged it with. For example, if I want to create a new container on my Mac and just run an application from a container image, I can just use the Docker command, the Docker run command, to create and start a new container. I'm just adding a couple of parameters that you should not worry about, so don't worry, I'll explain all of the stuff that I'm doing here in much more detail in a few minutes. I just want to demonstrate how easy it is. For example, now we can pick a container image that we want a new container process to be created from. For example, I've installed a Debian image, an Alpine Linux image, some other testing applications that I'm running here, Nginx web server, a database. For example, for now, let's just create a new container from a generic Debian image, and once I hit enter, you can see it automatically starts a new shell. So this shell is not running on my Mac system anymore, so this is already running in a Debian-based container. For example, when I cut the output of the etc. OS release file, you can see that this container thinks that it would run on a Linux distribution that is Debian 2 bookworm. And I could also easily just create a new process. For example, when I open another terminal window and I execute the exact same command, you can see I got a second shell with a different ID, because these are two separate containers and they don't really know about each other. For example, when I show you the file system, you can see that each of the container has its own file system. For example, when I create a test.txt file, and you can see it's present on the container 1. And when I check the file system on container 2, you can see that the test.txt file is missing in here, because the file system on container 1 is different from the file system of container 2. And that is also the case for all of the processes and things that are running inside the container, such as the apps, the binaries, and the libraries. But one thing is really important, and I should mention it at this point, because you might know, oh, this looks like a virtual machine somehow, but containers are not virtual machines, because containers, they don't come with a full-blown operating system. They only come with all the necessary tools, binaries, and libraries. For example, on a Linux virtual machine, you would be able to execute commands like ps. No, this is not present in that container image because it was created with the idea in mind to be as small as possible and only come with the necessary tools. For example, if we take a look at the binary folder, you can see that it has a couple of generic Linux utilities and tools that are present in that container, but not like in a full-blown operating system. But let's take a closer look at the architecture and how Docker approaches containers to better understand how these different components interact with each other. So if you want to create and run containers on your host operating system, you will always need a container engine. And Docker's implementation requires a daemon. So this is a service application that always runs on the host operating system, and this is responsible for managing containers and container images. And if you want to instruct the Docker daemon to perform certain actions, so if you want to build a new image or create a new container, you will need a CLI tool, so that is the Docker CLI, which is a terminal application you usually install on your client. Note, the client and the host, they don't necessarily need to be separate physical machines or virtual machines, so you can install the client, the Docker CLI, on the same server as where you're running the Docker host. But you could also technically install that on a different machine or make API calls to the Docker daemon from a different client. So that's why I always refer to it as a client. And the CLI tool, as I said, there you can execute the Docker commands. Let me quickly explain some of these basic commands. So these are the typical commands that you will always need when you want to work with containers. For example, the docker build command. So this will build a new container image. As I said, a container image, that is this lightweight package where all the files, the binaries, the tools, so everything that this container and its applications need to run with. And this you can directly build with the docker build command. And once you created a container image, you can start a new instance of a container, so a new container process from that image. And as I said, you can run multiple copies of the same image on the system. And then you will use the docker run command that I just demonstrated to you. But you might also think, when you build these images, how do you ship them or how do you share application images? So that's why we have a third component, which is very important, and that is called the container registry. So a container registry is like a big cloud storage where developers and individual people can upload their container images. For example, there are container images around that are based on a Linux distro, something like Ubuntu, or are packaged with fully pre-configured, pre-installed applications, for example, an Nginx web server, or some other apps like Grafana, Drupal, Teleport. There are millions of different container images existing and uploaded on the Docker Hub, which is one of the container registries that is around. And if you want to start a new container from a specific image because you want to run an application, you can just use the docker pull command that will automatically download that container image. Then with the docker run command, you can start new containers and multiple copies of these container images on your host system. And that's basically the whole magic behind containers and how they work. I know there are many, many more details we could talk about, but I think this presentation was already long enough. I hope I didn't bore you with that presentation, but I think it's really important to understand the bigger picture before we start playing around with containers, so you actually understand the reason and the whole architecture behind it. Now, if you want to easily get started with containers, I would always recommend you to start with Docker, because Docker is one of the earliest players in the container business, and they created a lot of great tools and utilities and services around containers that will make it very easy for you as a developer or as an individual person to get started with containers completely for free. And what I would always recommend you as a beginner, if you want to play around with containers on your personal workstation, on your computer, you should always install the Docker desktop. So this is an application that comes with the Docker engine, so that Docker service daemon that you will need to run containers, but it also has a graphical user interface. It also has some other interesting utilities and services around containers that help you to easily maintain containers on your system. And it's also pretty clever because Docker Desktop allows you to run Linux-based containers on a Windows or on a Mac system as well. Because these container images don't actually contain a guest operating system like virtual machines, you're not able to mix operating systems, you're not able to run Linux-based containers on a Windows or on a Mac machine. So the Docker Desktop system on a Mac or on a Windows will install a small, lightweight virtual Linux machine in the background. You don't need to manage this. So Docker Desktop is doing this entirely for you. But this small virtual machine, that is a Linux-based operating system, and this is where the actual containers are executed in. For example, this is the Docker Desktop that I've started on my Mac. You can also give this virtual machine resource allocations or customize how many CPU cores, memory the system will reserve for that virtual machine to execute your containers. You can also easily customize all the configuration, install software updates. You even have extensions. You can easily manage all your container images, your volumes. So this is really a great way to get started. However, on my home servers, like my Ubuntu servers, they don't have a graphical user interface, so I don't really need that Docker Desktop. I just need that Docker daemon, so the engine. And this is where you should go to the documentation. So this is also a great place to learn more about Docker and use as a reference for all the CLI tools and manuals. So here in the manual section, you will find a guide to install the Docker Desktop, but you can also find a guide for the Docker engine. And if you want to install the pure Docker engine, the Docker daemon on a Linux operating system, you would typically pick one of these server packages, either in the Debian or RPM format, depending on what type of Linux distribution you're using. You can also easily find instructions. For example, I'm mostly using Ubuntu Linux distros on my home lab servers. And there you have great instructions and terminal commands, so how easily you can install the Docker engine on your machine. And then if you have done all of that, if you are running this on a Windows, on a Mac based in a virtual machine, and the Docker engine is present, you can execute commands in the terminal. By the way, there's probably one thing for the Windows users that I should mention, because Docker Desktop runs in combination with WSL2. So this is the Windows subsystem for Linux. And I've used that in some of my older videos where I was using Windows. So now I don't have a Windows machine to actually show it to you anymore, but you can check out my older videos on YouTube where I've explained this in a bit more detail, or just go to the official Microsoft homepage and learn how to install Linux on Windows with WSL2. And then you can install Docker Desktop on top of this, and you can select your WSL2 instance that you want to use to run and perform these Docker commands. Okay, so let's go back to the terminal. So if you've got that installed on a server or on your workstation, you should be able to execute the Docker commands. So this will give you a list of all the different commands that you can use. Don't worry, we will go through most of these basic commands here in future video series, so I'm not going to explain everything in this short video. This would fill out multiple hours for sure. But we will start with a very simple Docker version. So this, if you execute this, you should see some output, and if that works, you can be sure that the Docker engine and the Docker CLI has been installed correctly on your workstation or on your server. Now, again, to start and create a simple container I just explained to you, you can use the Docker run command. So this is probably the easiest way. And let me just do that with a short example. There's a small container image that is maintained by Docker, which is called Hello World. And if you start this container, it will just print out some stuff on the terminal to demonstrate, okay, Docker is working properly. And then you can see it immediately stopped this container. But you can also start, like other containers, with an interactive terminals. So this is what I've just used for the Debian container, interactive TTY. But for now, let's not start a Debian-based container image. For example, I've also installed an Ubuntu base container image. You can see this is even smaller, just 69 megabyte. And when I start this, it also starts a new shell. Maybe you just want to try out something else, for example, CentOS. This container image seems to be existing, but it's not present on my system because I haven't downloaded it with a Docker pull command. So if you try to start or create a new container with an image that is not present on your system, it automatically pulls it down from the container registry. Now, one question you might have is, where do you actually pull down these container images? Where do you find them? And this you can easily find on the Docker Hub registry. You just need to go to hub.docker.com, and there you can search for specific container images. Just like I said, there are container images for Linux distributions, something like Debian, Ubuntu. So these are usually small, lightweight core images that you can use as a template, and you can extend with your own applications and deployments. But there are also other ones existing. For example, what I often see is the Alpine Linux distribution. So this is much more lightweight than Ubuntu or Debian is, and that is really often used as a base image for new container deployments. But you can also search for specific applications. For example, if you want to deploy an Nginx web server here, you can see Nginx, or the developers of Nginx, they also maintain their own official build of Nginx in a container image. So these container images are based on those core images, like these here are based on a Debian bookworm or on an Alpine Linux distro. And you can select container image tags that you want to start your container from. And those tags are shipped with different versions of Nginx, or they are based on different Linux distributions or core images. Let me just demonstrate this example. So for example, we want to download and start the Nginx web server in a new container. I'm just searching for this app and I see, okay, so this was maintained from the official developers of Nginx. Be careful when you download container images, by the way, because you can see some of the container maintainers or developers are verified publishers or are Docker official images, but not every, because you could actually build your own container image, install an Nginx web server in that image, and upload it to Docker Hub. So this is where you can see so many different flavors of applications and container images. So you can see these are sponsored OSS, but you can also find container images from individual people here. So for example, this is from someone who's uploaded a container image that's called Nginx Gate, and that was updated 6 years ago. So this is, for example, nothing that I would want to deploy. So you really need to be careful when using container images. The most secure way is to build your own container images. So we probably do this in upcoming series here. But for today, I think it's totally fine to just use one of the official images. This is, by the way, the way how most system administrators that are not software developers just run the official application container images, and they are totally fine with it. So just to mention. And for example, I just want to download this here. I can just write down this tag here, and I can execute the docker pull command. So if I just pull down the Nginx container image, it will always use the default tag latest. And as you can see, this is up to date. I've already downloaded and installed this latest version. So the latest tag is usually updated by the maintainer once a new version of that container image is released. But I usually also say, like, the latest tag. I don't know if that's the best way to deploy applications. Most of the time, you will pick a specific version to make sure it's compatible with all the other systems on your infrastructure. So let us pull down this specific tag here. So if you write the name of a container image, the tag is described after a colon, so 1.24.0. And let's pull down this specific container image. And now that we have this container image, you can also inspect what are the images that you have currently downloaded on your system with the docker image ls command. So there you can see I've downloaded a couple of images. Somewhere should be Nginx. So here you can see I've downloaded Nginx 3 times, but I've downloaded it in 3 different tags. So here's the version 1.24 that we've just downloaded, but I also downloaded the tag 1.25, and the latest tag is also separate, but you can see the image ID is the same here, the latest version, with the 1.25.2. So that means even when these are different container images, they actually contain the same payload. So that's how you can sometimes see, so this is actually the latest version. And of course, you can also remove older images from your system. So if you want to remove an image, you can execute image rm, and then you need to give it the ID here. Or the short command would be docker rmi. So this is the short version, for example. Let's delete some of these test images that I've built. Don't really need them anymore. And then I've cleaned up a bit this list here. Note, we will talk about Docker images and the different layers and how to tag and build them in probably the next video of this series. For now, I just want to teach you more about how to create and run containers. So for example, if we want to run a new container instance from a specific image, again, use the docker run command. Then you can use the image and then specify the tag, for example, latest or the 1.2.5.2, hit enter. And then we've just created a new container from an Nginx image. So this is the web server that is currently running on our system. Now, let me just stop this. And if you want to see what containers are currently running on your system, you will use the docker ps command. But as you can see, there is nothing in here because there's currently not a single container running on my system. With the docker ps --all flag, you can get a list of all containers that are currently existing. And if you create these containers and you stop them, they are still existing on the system. Just like this Nginx web server that I've just started and stopped, it is still present. And if I would execute docker run nginx, you can see this will not just start the same container, it will create a new instance with a different ID. And if you want to start the same container that is existing, you will need to use a different command that is not the docker run command, but the docker start command. And then you need to give it the name of the container, the ID, and then we can see docker ps. So this container is currently running. Of course, we can also stop this container again to give it this ID. Then our container is stopped. And you can also do things like restart a container, for example. And if you want to remove an existing container from the system, you would use the docker rm command, just like with the images, give it the ID, and then your containers are gone. Okay, so we now understand how we can create and run new containers, how we can stop existing ones, how we can remove existing containers. Now let's get in a bit more details here, because this is probably what the bread and butter of a system administrator is. If you want to deploy and run containers in your home lab or in a production system, you should actually know how these containers function, how you name them properly, how you can inspect the configurations of these containers, how you can start them with flags, how you deal with network access and persistent storage. I don't want to go into all of the details because I will probably create one video per each of these topics separately, but just to get you started so you know enough to run them. Now, first, if you want to inspect the current configurations or details of an existing container, you will use the docker inspect command. So this is very useful to get more information about a specific container. For example, if I want to get more information about this Nginx container here, I can just execute the docker inspect command and use the container's ID here, for example. And then I get a JSON object list of all the different configurations or flags that this container has been started with. You can see the container's name, the arguments, you can see the status that it's currently not running, or you can see the SHA value of the specific image that this container was started with. Many more configurations. You don't need to understand all of this stuff yet, but it's important that you can find more information about your existing containers with that command here. So let's go back to this list here, and let's assume I would want to run an Nginx web server on my system using Docker. And I want this to be a production-ready system. So how would I approach this? And there are some important flags that you need to start your container with, such as network access, persistent storage, and so on. For example, if I want to create a new Nginx container, let's start with a very simple thing. I will use the 1.2.5.2 container image tag, but I don't want this to be generated with a random name that doesn't say anything about this web server, yeah? So I want to specify the name. In this case, I would use the --name parameter, and I can give this web server container a unique ID. For example, Nginx production 1, for example, yeah? Just pick a name that you like and where you can recognize your existing containers. And because this container always runs in an isolated environment, we also need to allow access from outside to this container. So we need to publish the network ports. And this is done by using the flag --publish or just -p, that's actually the same. And then you need to name the ports that you want to publish or allow access from outside. So you should know a web server like Nginx usually uses port 80 and another port 443 for HTTPS. And as you can see, you can just give these port numbers. The colon differentiates the host port from the containers port. So this is really important to understand, because the application process inside the containers file system will usually use the port 80 for HTTP and 443 for HTTPS. That might be different for any type of application. Yeah, a database uses a different port that its service is listening on. But you can also map the port to a different host port. So for example, inside the container, Nginx is listening on the port 80, but you want to publish it on a different port, then you can just change the mapping on the host system to a different port, something like 8080, for example. So then you map your host operating system port 8080 to the internals container service port 80. And the same you can do for any other port that you want to publish. For example, 443, you can change to 8443. That is what you usually do when you have more than one container trying to listening on the same port. You would need to change the port number on the host OS without having to configure the application inside the container. So very useful. And because the storage inside the container, you might have a container deployed in a version 1.2.5, then you download a new version of that container image. You need to create a new container with that new tag. How do you transfer the data from the first container to the second container? This is why we use persistent volumes. So we use a Docker volume with a -- volume parameter, and then you can use named volumes or you can use mount points. I'm most of the time using mount points here, but I will probably make a separate video about persistent volumes. I have also done some videos in the past, so if you're curious about these differences or how do you migrate data from one container to another, you can still check out my older videos. So here I will, for example, and that's the same principle like with the port numbers. You can map one specific file path on the host operating system. So this is on my Mac in my personal home folder, tutorials, Docker tutorial 2. And let's for example, pick the HTML directory and map this with a colon to the internals container file system. So all the HTML pages inside the containers file system, of course, need to be in a different location. But this is how you can easily map persistent data storage on your host OS to a specific path in the internal containers file system. For example, here we can use the user share Nginx HTML location. So this is where the HTML locations are stored. And what we can also do is we can run this container in the background, because if I would start this container, I would open a shell, and if I stop this shell, the container would stop. So if I want to persistently run this container in the background, I would attach a -d parameter for detach, hit enter, and then you can see the container has been started. If I execute a docker ps command, so now I can use a simple ps because the container is currently up and running, you can see it has these port mappings. Port 8080 is mapped to port 80 inside the container, and 8443 mapped to 443, and the container is up and running. So now we can try to connect to this web server with a simple curl command on the local host, but we need to use port 8080 because this is the port what we have mapped to. And you can see the response is forbidden because probably there is not a single file existing in that folder. So let us quickly open this location. And for example, let's create a new file in here that's called index.html. So that's the default HTML website. I just want to let's just add some random data. I think that should be totally fine. Let's go back to the terminal and let's execute the curl command again. And you can see that's our web page. So this is how we easily deployed a web server in Docker. And now if we want to stop this container, we can easily use docker stop command. And now we don't need to get the identifier. We can use the name that we have specified. So let's stop it. Let's check docker ps --all. And now we still got our container with the name Nginx production 1 in that list here. It's currently stopped and it's created from that image. Now, when I want to update this to a newer version, for example, to the latest version, what you would typically do is you remove this existing container. Don't worry about it, because we've still stored our index.html file in our host operating system's file path. So when I create a new container, and I can now just change the image tag and update this to version latest, for example, I will use the exact same command and mount the same data that is persistently stored on the host in the new containers file system. I will publish the same ports, nothing more. Let's just start it. And as you can see, container is up. So this is how you would update your application. You just stop the container, delete it, and create it with a new image version. And this is much easier than you having to go inside the container, update the packages, make sure that the migration has been successfully done and so on. No, you just use the latest image tag deployed and maintained by the software developers of Nginx. Just check out if there is a new version and then create a new container with the exact same command like you've used before. So this is how you can easily get started with containers. I know this was a lot, and I hope you will try it out at home. You will just start installing Docker Desktop and just start playing around with it, create a few containers, try to deploy a couple of different applications, and try to familiarize yourself with publishing ports and persistent volumes. Try to store data persistently in a specific location on the host system and mount that in a container. This is how you usually can get started with it. And we've just scratched the surface here. So again, this was the first video of a brand new series. We will talk about all of these things like building our own container images, about persistent volumes, managing projects with Docker Compose, and we might even talk a bit about Docker security and vulnerability scanning. So there are so many cool topics we can talk about. Also, not to forget Docker Swarm. So there are a lot of great ideas I have in mind. You just need to be a bit patient with me creating content because it's usually a lot of work. Anyway, if you want to support that work, so if you enjoy these free tutorials that I'm creating here, don't forget to hit the like button, subscribe, and if you want, you can show your appreciation by supporting me on Patreon. Thank you so much for all the supporters on Patreon. It's really helping me a lot. Thanks for watching. I'm happy that you're here, and I will catch you in the next episode of this series. Take care. Bye-bye.